And thank you all, welcome, and thank you for attending. Since you mentioned, I put this here because there's a webinar that we did that is based on the talk I gave at this workshop, and there's some additional information in there where if you find this material interesting, you can go to our website, you can find some more there. But we'll talk about the impact of additive phase noise on the design of frequency multiplier chains, and a great way to demonstrate this is through a SATCOM pot converter, and you'll see why. So we're going to focus on a military Ka band converter. That it's a reference design. We didn't do it for a specific application. We did it just to showcase some of the components and things that people ask us about all the time. But it's a great vehicle for demonstrating the effects of amplifier additive phase noise. So that's why we picked that as our technology demonstrator. So I'll start out. I'll just talk briefly about the buck reference design, the block diagram. We're not going to spend a lot of time there. I want to talk about the phase lock loop schematic a little bit more, because a lot of the effects that you're going to see are hidden a lot of times within under the noise of the PLL. So a lot of what you're seeing, you may say, I've done this 100 times, I've never seen it. A lot of this depends on the loop you're using. If it's a digital loop like we have here, some of the effects are going to be hidden underneath the divided noise. But so it's good to understand what you're using for a phase lock loop and whether some of these effects apply. And even if they don't, it's good design practice anyway. So it still pays to understand some of what we're going to be reviewing. We did a brass board implementation, mostly because we have all this available at many circuits, but I encourage you to use them as well. It's very informative. We're going to go through, use that to do some spectral analysis. I'm going to spend a little bit of time on filter technologies. We have some kind of unique filters at many circuits that I want to share some applications with you. Then we're going to go into the additive phase noise theory. If you are familiar with Professor Rubiola, no, yes. If you're not familiar with Professor Enrico Rubiola, rubiola.org, and you're interested in this material, then I suggest you check out his website. It's just a wealth of information. We're going to go into some cascade design theory, and I don't know if anybody went to Howard's lecture earlier. A lot of what you saw there, what you're going to see again here. And there actually is a design methodology. Oh, well, my old friends are here for designing cascade and amplifiers and having the impact of additive phase noise minimized. We'll look at some frequency multiplier effects, and then I'll show you some references. So that's the block diagram. We have we have a high dynamic range L-band variable gain amplifier section that provides IQ inputs to our IQ up converter. These are all mini circuits parts, in case you're wondering. The output feeds a variable gain RF section, and then we have a cavity filter that filters out some of the spurious that we'll see. We're going to focus on this multiplier chain here. We have a 14.5 gig VCO. It's a MMIC-based VCO. It happens to have a half frequency output. We send that down below to the loop. We lock our loop to the half frequency output. That means you get a lot of spurs on here. We'll talk about that. And then we're going to focus on this amplifier chain driving the ×2 multiplier. And you can see it's a combination of fixed pads and what we refer to as reflectionless filters. And if you're not familiar with them, you can think about them as frequency selective attenuators. They do not reflect the signal. The return loss into a reflectionless filter is good. So you're absorbing in the reject band within the filter. You're not reflecting that back. And that's very important when you're doing something like this, where you don't want this stuff feeding back into the VCO. Then we're going to talk about in depth, in gory detail, cascading these two amplifiers from minimum degradation to additive phase noise. We'll look at the final output here and what this section, how that contributes as well. Because as you go higher in frequencies, you'll find that the gate length gets smaller and smaller and smaller on some of these p-amp amplifiers. And as that happens, your 1 over F noise degrades. So you have to be careful, even back here, that you're not affecting the overall phase noise performance. So where's Chris? You can leave after this, okay? Again, I wanted to point out we are using an ADI integer and PLL. Okay, Danny? Danny helps us out a lot. and an active loop filter, and a mimic-based VCO. So again, I'm pointing this out. I'm not going to spend a lot of time here, because if you were using a DRO or some other lower phase noise oscillator, a CRO, right, Charlie? And if you were using a sampling phase detector type loop, you may start to see some of the effects that we're going to be discussing next. So it's really application specific. It doesn't mean you should ignore them, but you should at least be aware that just because you're not seeing them doesn't mean they're not there. And I really want to just acknowledge the help we got from the folks at Axtel, because they really went out of their way to develop this phase locked XO for us. It takes a 10 meg external input, because SATCOM guys love to use their own 10 meg, and locks an internal 100 meg. We go into here, we divide by 4, so we have a 25 meg comparison frequency that goes into the loop. So again, just want to thank Chris and the folks at Axtel for really helping us out with this, Joe. So this is the ADS block diagram for everything. You notice we have numbers 1 through 10. I'm going to measure frequency content at each of these nodes. So we'll look at the desired and the spurious signals that we see at each of these nodes. And that's going to help us design the filtering that goes with this. And we did that, there we go, using our press boards. Now, if you are interested in a mini circuits mimic amplifier, for example, you go to the web page, you'll see the part. If you go down to the bottom, it'll say something like, would you like to buy an evaluation board or a test board? They're useful. Go ahead, use them. I don't like them because they're very cumbersome. All right, they're not really designed for integration into a setup like this. So what we've done is we've taken pretty much every mimic that exists and put it in a connectorized assembly. So these ZX60s you might be familiar with. I think Tom is very familiar with ZX60s. You hook up a voltage, you connect it, and it works. It has the bias tees, the DC blocks, the regulation is all in there. If you see an LPN extension on a ZX60, it's a low phase noise model. You can use the test boards. Like I said, they're useful, but they're cumbersome to use. But the choice is up to you. I just wanted you to know that you might be able to find a connectorized, which is just easier to work with. So in any event, everything you see in yellow here, the loop, the VCO, the yellow multiplier section, the mixer, and the Merenda IF, all got assembled onto this multi-layer board here. The L band we kept separately because we're going to morph that into different configurations. So what we've done now is, because we have this, we can measure power and spurious at each point that we're interested in. So I find it very helpful. So that's what this sort of weird looking curve is here. We start at the VCO output. Here's the fundamental VCO output, about plus 5 dBm. But it has all its friends here. So like I said, there's a half frequency output. So what you get coming out of the 14.5 gig port is 7.25 and all the harmonics thereof. So I don't want to put those into my nice broadband amplifiers, because they will amplify this and just create more phasing and distortion. So you don't really want that. Plus, you don't want to reflect that back into the VCO either. So we go through a series of what we call XHF. These are the reflectionless high-pass filters. Okay, and again, they don't reflect, they attenuate. And that's very good, because you don't want a lot of, some of these signals are fairly high level. You don't want them reflecting back into the VCO. You'd like to attenuate them. People sometimes use large attenuator pads, but you're taking a hit and loss there. The reflectionless filters allow you to have a pass band that's low loss and a reject band that looks like a high loss attenuator pad. So they're very useful for applications like this. So we'll measure some of these, some of these points here. You can see the filtering. We go back through two LVA. We have two distributed HBT-based amplifiers that we use in this path. They have very low additive phase noise. They work very well. And we have two of them cascaded with a pad in between. And that should be considered a building block. Amplifier, pad amplifier, when you cascade these, because you want to make sure that you can control the input power into each stage so that you get the performance you think you're going to get. And we'll go into that later. At this point, we go through a final reflectionless low-pass filter, which is in front of the times 2 multiplier. So any harmonics coming back from the multiplier will be attenuated rather than just reflected back in. Don't forget, when you look at the data sheet for some of these parts, they're measured in 50 ohms. You put a reactive load on one side, you're not quite sure what you're going to get. So the reflectionless filters ensure that you've got basically good 50 ohm loads on each side of your nonlinear element. And the idea is to maximize the isolation from any nonlinear element back to the VCO. We go through this final amplifier here, which is a 0.15 micron PM. We'll talk about him later. At these frequencies, you're going to be stuck. You're going to have to use a PM. And you might have to use a 0.15, 0.1 micron gate length to get the gain that you need. But these are not great for phase noise, as you'll see. So at this point, this is the LO input to our IQ mixer. We introduce a 1 gigahertz tone. At this point, it comes out at 30. Our LO, as you can see, is 29. And then we go through our cavity filter, and you have the desired upper sideband, you have the LO leakage, and you have this in-band spur. Ka is very nasty because the second harmonic of the 1 gig falls in-band, and it's subjected to the minus 60 dBc spur requirement. It's very difficult to get rid of that. And it can be caused by a few different things that you may not consider. I mean, obviously, a second harmonic in the L-band amplifier will just map right through. We don't have that. Our L-band amplifier is extremely clean, and our attenuator is extremely linear. So you look at some of the mimic-based attenuators, and you vary the attenuation level, and you watch your harmonic moving. This won't do that. So we know it's not coming from there. It could be a 2x1 in the mixer, right? We know it's not that. But it could also be a third-order product, and this is what gets some people. It could be a third-order product between the LO leakage and the upper sideband, right? Causing a 31 and a 28 gig tone. And what you're seeing here is actually the result of third-order distortion, either in the mixer or in the amplifiers that follow. So you got to be careful about that LO leakage. We have nulling pins on the IQ inputs that we can use to balance each mixer, and that'll attenuate the LO or reduce the LO leakage, and that tends to reduce the spurious also. So I didn't put data in, but we can get this down to minus 60 dBc. All right, now we're going to talk about, as I've already mentioned ad nauseum, right, reflectionless filters. So if you go to our website, you can download for free any S parameter model you want, all right? They work pretty well, all right? Here's the measured, here's the modeled. They agree very well. We also have certain behavioral models available for some of our amplifiers, mostly X parameter behavioral models. We work with monolithics to generate some of these behavioral models. If you're interested in one and you don't see it, go to monolithics. Maybe it'll be there. If not, call us. We're in the process of generating for ADS, amplifier 2 and amplifier S2D behavioral models, which basically takes the information we have published on the website, but condenses it into a model that you can use within ADS. So if you're interested in that, we're making those available. We just released a blog that kind of gives you the instructions if you want to do it yourself. So you can create these behavioral models, and you can do I don't have any data here to show that, but you can do harmonic balance simulations now, and you can do 2 tones, first order, gain compression, in ADS rather than my favorite spreadsheet, but I'll never give up my spreadsheet. So I want to look at some discrete sections of this. So we're just going to look at the passive front end of this right now. You can imagine this is a broadband amplifier. It works basically DC to 27 gigahertz, so it looks like a broadband load anyway. You have some attenuator pads. Here's our first reflectionless filter, another attenuator. Then we have this, when you see this type of designation, this comes from a micro ceramic team. It's a conventional reflective filter built with LTCC technology. So we need to incorporate that within this chain and then a final high pass. So we'll go into that. So the reason you see this filter here is because the strongest spur coming out of this VCO is right here. It's the 7.25. We don't want to reflect that back in. So if you look at the combined response, look, we have 6 dB of loss and we have 67 dB of rejection, but it's got about a 15 dB return loss. Okay, so the spurious goes into the filter, gets absorbed within the filter, it doesn't get reflected back. That's very important when you're designing these multiplier chains. You want isolation back to the VCO. You don't want these nonlinear elements modulating the load back into the VCO. So this is a great filter to use in this application. Whether you've heard of it or not, I don't know, but I personally like them, as you could tell. All right, so that's here. We come into the pass band of both the high pass and then the microceramic low pass. The microceramics are going to have much better rejection, much closer in. So the reflectionless tend to have a little bit wider reject band. The microceramic filters are very sharp. So that's why we used it here, because those spurs are much lower. I'm not as worried about reflecting that power back into the VCO. Plus, there's loss back here. So you still see better than a 6 dB return loss. So it's not like you're just reflecting everything back off. You look at the output of this filter and you go in ADS and look at the return loss. Look at the return loss you see in the reject band. It's like 0 dB. All right, they're very good, but that's how you get this rejection band. The reflectionless filters absorb that. They don't reflect it. And then you notice I have another XHF on the output, and people will discuss that. Why do you put that on the output? Well, because it's in front of this LVA. It's in front of this very broadband amplifier. Now, do I want to test the unconditional stability of my amplifiers by presenting basically a 0 dB return loss on the input? Yeah. I'd rather not. All right, I'd rather not test something like that in a system I need to deliver. So when you put something like this here, it's matched in its rejection band, so that's fine. In the pass band, it's matched, as you can see. In the reject band of the LFCW, though, at least you get a little bit of load buffering from the insertion loss. That's how I like to think of them, as a frequency selective pad. All right, so when you're working in the reject band of this filter, this is in the pass band, so you get maybe a 2 dB round trip return loss. So that amplifier is not looking into 0 dB return loss. And believe me, a couple of dB helps. So that's a good technique that I like to use. I actually put one here so it provides some buffering from the reactive filter. Then we're going to go into ad nauseum later, as you'll see, this amplifier cascade. And again, the pad in between, I think, is a basic building block. You should think about this as not just cascading amplifiers, but cascading so that you can control the input power into each amplifier. So there's another guy here. I just love to use these things, right? I don't get extra money if I use them. But the same thing. You have this ×2 multiplier following that. It's nonlinear. You don't know what the impedance really is, it's going to have harmonic content that's going to come back. Well, this will absorb it rather than just reflecting it back in and having these spurious signals bouncing around and giving you ripple, giving you amplitude fluctuations, phase fluctuations. So it's a great way to terminate, again, as a frequency selective attenuator. And the measure diversity model is fine. What you're going to find is that cascading amplifiers is bad. All right, we're going to talk about this ad nauseum later. Cascading amplifiers causes your flicker noise to increase by 3 dB log base 2 of n every time you cascade amplifiers, and I'll go into why that happens later. So you have to be careful when you do this, and just cascading them is kind of naive, because you really want to be able to control the input power into each amplifier, as opposed to just running a cascade and letting the input power to this next stage be whatever it wants to be. So you want to control that, as we'll see. So we'll get to some phase noise theory now. And again, if you're not familiar with Professor Rubiola, nobody here's heard of Professor Rubiola. You have, right? I know Charlie has, right? Very nice guy, right? He invited me to his conference in June. So these are from his seminal paper, really, back in 2012, where he came up with the theory behind cascading. But I just want to go through these quickly. Because there's notation that us microwave types don't really use S. We don't use S. So let's just go through each of these a little bit in detail. This is power. This is your spectrum analyzer. Okay, this graph here is your spectrum analyzer. You're measuring power in dBm on the y-axis and frequency on a linear axis. and you set your span to be something, and you set your resolution bandwidth, right, to be something of interest. Of course, you adjust the amplitude. So when you do that and you look at your spectrum analyzer and there's nothing hooked up, just maybe a 50 ohm load, what do you see? You see something like this red line. Now you see the noise floor of your spectrum analyzer. All right. Then what I'd like to do is go into my lab and take a really clean synthesizer, and inject that into the front end of my spectrum analyzer and slowly turn up the amplitude. What am I going to see? I'm going to see a signal coming up, and as I increase the level, my signal to noise ratio improves. The noise as filtered by the resolution bandwidth. But you basically see that. You see the synthesizer emerging from the noise. That's why they call this additive, really, because the signal and the noise are adding. Then we're going to change things up a little bit. We're going to take our amplifier under test. We're going to connect the output to the input of the spectrum analyzer. We're going to terminate the input of the amplifier with 50 ohms. And we're going to just turn the DC on to the amplifier. What do you see? Well, you see something like this blue line, right? This blue dashed line. You see the output noise power of your amplifier. If you went to Howard's talk earlier, you know all about this now. But then we're going to do the same thing. We're going to take that synthesizer and connect it to the input of the amplifier and slowly increase the signal amplitude. And as we go up, we notice something. We notice something we didn't see originally. We see sidebands appearing on our carrier. And those sidebands are the result of a parametric up conversion of the amplifier's 1/f noise, which is a near DC. It's a baseband process, follows a 1/f power law that gets frequency up converted to that carrier. So whether you like it or not, you're going to get sidebands when you pass a signal through an amplifier. And these sidebands that you see here are a result of this flicker noise being up converted to the carrier. Ultimately, that meets the white noise floor that you started with. So that's your spectrum analyzer. Then we go to this instrument here. This is a different instrument now. S phi of F is the double-sided power spectral density of the random phase. What is that? That's a mouthful. It's a power. It's measured in dB rad squared hertz. Again, we're microwave guys. We don't use rad squared hertz, but we'll talk about that later. What's important is that this represents a power expressed in dB, or, well, let's just say this is a dB scale for right now. The units are actually dB rad squared hertz. And you notice there's two sets of curves here. This blue line, this is the 1/f spectrum being converted to about the carrier frequency. I didn't mention the x-axis, forgive me. This is obviously frequency, but it's on a log scale. So you've got log here. Similar to what you would see off a phase noise analyzer, but this is not a phase noise analyzer yet. The frequencies you see here are formally referred to as the Fourier frequency, but for our discussion, and since we're microwave types, we're going to violate that a little bit. We're going to call this offset frequency from the carrier. So this may be 100 hertz, 1 kilohertz, 10 kilohertz, 100K. And this line, this 1/f noise, is completely determined by a single parameter, this B sub -1, the flicker noise coefficient. If you know that, you know the entire behavior of this spectrum over offset frequency because it follows a 10 dB per decade slope. So all you got to do is find out one number and you're all set. It's not that easy. But if you know this one number, then you know that you know the shape of this response. And that's going to continue to roll off until it hits B sub 0. B sub 0 is the double-sided power spectral density in the white noise region. Now, I'm glad Howard's here. Everybody should know what this term is. Who doesn't know what FKT is? All right, I'm sure you do. All right, very important. If you're a microwave guy and you're doing system analysis, you live and die by this term here. You know exactly what this term is. So what excites me about this is that you're seeing standard cascade microwave theory brought into metrology theory in a form of FKT. So this is the power spec. This is thermal noise. This is minus 174 dBm per hertz. That's what this is in a 1 hertz bandwidth. And it's divided by the input power to the amplifier. So it's kind of like a reverse signal to noise ratio. So as first time you look at higher power, I get lower. No, yeah, because it's in the denominator. So this is important because that's why I was focusing so much on input power, because depending on what your input power is, you're affecting the power spectral density in the white noise region. So if you're arbitrarily just assuming a power, you could be up here. But why not operate here and maybe put a pad afterwards? So we'll go out and talk about that in more detail. But again, we don't use S, we use L. L is the single sideband phase noise, not the double sideband power spectral density. We use L, the single sideband phase noise. So if you want to work in rad squared hertz, it's just 1/2. If you work in dB rad squared hertz, just subtract 3 dB and you've got single sideband phase noise in dBc per hertz. And again, us microwave guys kind of take exception and we say, all right, dB below carrier. That's not the fundamental definition, but it's good enough for what we're going to discuss here. And we just use it, so we might as well just accept that. Then we go into just some cascaded theory. Again, we talked about this earlier, where the 1/f noise will add as a power. It adds 3 dB log base 2 of n, where n is the number of stages, or m. And why is that? Again, you can see you have your perfect tone. You put it through the amplifier. The 1/f noise is parametrically upconverted to that carrier. That goes through the next stage. Well, how do those noises add? They add using power addition. So you can convert to, it's like v squared 1 plus v squared 2 square root, as opposed to the parallel case. So you have that's why it's 3 dB. It's power addition. If you go to the parallel case, it's a little bit different, right? The signal splits. You get two equal tones. They go through the amplifier. The 1/f noise for each amplifier gets parametrically upconverted to that carrier. But then they combine. How do they combine? The signals combine coherently, voltage addition. V1 RMS plus V2 RMS. The noise combines with power addition. V1 square RMS squared plus V2 RMS squared, square root. That gives you a 3 dB delta. So here you get a 3 dB log base 2 of m improvement in the 1/f noise when you put in parallel, a degradation when you go in series. It's important because if you're designing a system and you're concerned about additive phase noise, it's nice to know that. So I don't know how I'm doing on time, but I think we're moving along.
What
time is it?
So you got about a half hour.
Oh, okay. All right. I think we're all right. That was a long slide.
Stood.
But it's important. So again, why do we care? We're here, so obviously we care about something. Hey, Adam. So if you're doing comm work, we all know phase noise rotates the constellation. If you're an amplifier guy, if you're an oscillator guy, you have to start with an active device. You have to start with some kind of sustaining amplifier. So you need to know that this amplifier noise will get mapped to the oscillator noise through the Leeson effect. And you can see an approximation for it here. So if you're a comm guy, an amplifier guy, if you're a particle accelerator guy, man, I was blown away by the types of jitter that they look for in time. It's orders of magnitude lower than anything I've ever seen. So these guys are really, really, really concerned about phase noise. And we all know that when you integrate your phase noise curve in across these decade bandwidths, you integrate that, add it, you can convert that phase noise to time and phase jitter. So we all know that. So it's important for a number of reasons. White noise, again, we should all know this term, right? If you do any kind of system analysis, cascade design, you're familiar with the term called the minimum discernible signal at the input. All right, we're going to set B to 1 hertz, and that makes the MDS FKT. We heard about this all. That's the minus 174 dBm per hertz that we all know about. All right. B sub 0 is then simply the MDS normalized to the input power. So it's the ratio of the minimum discernible signal to your input power. That's why when you raise the input power, this number gets less. If we take it through the output of the amplifier, we can define a B0 and an MDS at the output. It's just multiplied by the gain. And if you look at B0, the power spectral density of the random phase on the output of the amplifier, you see it's the same thing, just has a gain term, and it's P out. This leads to this kind of erroneous rule of thumb for additive phase noise, where you say, oh, if I get a part with high saturated power, I'm going to be really good. And I want really, really low noise figure, and I'm going to be really good. That doesn't really hold. First of all, this is only in the white noise region, not in the 1/f region. So we're going to come up with some real rules of thumb, but this is used, whether we like it or not. I don't recommend it, but it's a guideline. Obviously, if you have an amplifier and you need more power, you're going to have to go for a higher PSAT. But don't think that that's automatically going to guarantee you lower additive phase noise. What is 1/f noise? A little bit more complicated. It's anything that follows the 1/f power law. And everything pretty much in the world follows a 1/f power law. Not only electronic materials, pretty much everything. You could read papers and all kinds of things. They find phenomena that follow this 1/f. Look at your phase noise analyzer and just watch it, cross-correlate a bunch of times. You're going to get 1/f noise. All right, that's going to interfere with your ability to determine what your device's actual 1/f noise is. So it pretty much exists in everything. It's not unknown. I mean, there are two basic mechanisms that are used to describe how it's actually generated. The one that affects our parts and most of the parts that we use in the microwave community is trapping due to surface states. And there was a big controversy and rivalry between Huga, who came up with the conductivity due to fluctuations in bulk mobility, and surface states. A lot of papers back and forth, in fact, who's right, who's wrong. There is no right and who's wrong. So here's, for example, a paper that the authors derived an expression for the power spectral density of the 1/f process for their HEMT, for their high electron mobility transistor. And they did it in terms of the Huga parameter, which you can see is a function of a measured term. So remember I said B-1 has to be measured. Well, even in their theory, there's a term that has to be measured. So you can't really get away from that. And it's a function of the gate length and width in the numerator, which means this, if I make this smaller, this goes down, that improves. Our devices don't work like that. In fact, they're the opposite. So you have to be careful when you're reading papers where people derive expressions for this. A lot of times it's a function of their specific process, and that may be that, well, maybe in their application, yeah, it was bulk mobility. But I can tell you all the parts that mini circuits uses, and probably most of the parts that you're familiar with, it's surface states. It's not bulk mobility. So be careful when you read the literature that it actually applies to your device. What we can say with pretty much certainty, it is dependent upon DC current voltage, the device type. Is it a PHEMT? Is it an HBT? Process node size, well, what's the gate lengths? What's the emitter widths? All right, those all affect things. Power density is very important, and you'll see some rules of thumb that I have here for HBT devices. High area, in other words, you take the width times the length, number of fingers, and you get an overall periphery. And you run that larger periphery over the smallest current, you get the best 1/f noise. That's legitimate, that holds. And not all these rules of thumb holds. Again, if you're an oscillator guy, you already know about an unbypassed emitter resistor providing feedback to cancel some of the 1/f noise. So that still holds here. So which one is better, right? You're like, oh, PM, I want a 1 dB noise figure PM. I'm gonna get the best phase noise. We're gonna look at that. What do I want an HBT? Well, it's got higher noise figure. It's no good. We're gonna look at that. We have two blogs that are on our website that go into a little bit more about the physics behind the HBT and the PHEMT. And I'm not going to spend time on it, but the obvious thing is that the collector emitter current is flowing through the base region. And the base region is thin. It's on the order of 0.5 micron or so, kind of like the gate lengths of our PHEMTs. But the emitter width is fairly wide. All our parts use a 2 micron emitter width. Compared to some of these PM geometries, that's huge. All right, so there's one difference as opposed to the PM where the current, the drain to source current has to flow under the gate. And as these gates get smaller and smaller, as you saw, the 1/f noise gets worse because the trapping density increases. So you can almost look at this B-1 term, the flicker noise coefficient, as being proportional to 1 over the gate length. And that's how our devices behave. Now you can make up for that, right? You got a number of fingers and gate width, which you have at your disposal. But if those are equal, then the gate length is going to determine the performance in the 1 over F region. So here's another paper. This was actually done by NASA because they wanted to see what happens when you irradiate these SIGI HBTs. But what this shows is that, again, the larger area for a fixed current, larger area will have a lower power spectral density in the 1 over F region than a smaller periphery with the same current. And this is just a complementary way to look at the same thing, where as the periphery increases, this improves, and as the current goes up, it degrades for all three. So something to think about. All right, so some measurements. I'm not going to spend a lot of time here, but I want to point something out because it's common with our instrument. It may be with yours, it may not, I don't know. But what we found is you set the instrument to a specific carrier frequency, and you set the output power from the unit to a specific power level. And then what we'll do is we'll set these attenuated. This will be 0, 0. We'll make these at 0. So we get as much power as we can. We'll put a through in place of the DUT, and we'll just look back into the input of the analyzer, and we'll look at the response. And what we found is that for certain carrier frequencies and certain power levels, you get kind of a funny looking shape, which I don't really care for. So what we found is that if you reduce the amplitude on the instrument, say that ours can output plus 13 dBm. So you reduce that, make it plus 11, plus 10, and you look at the response. You'll find that there's a power level that gives you a nice looking through response. And you'll see what I mean shortly. Like, okay, you know what? That's it. I'm not touching it. I'm going to use my 11 dB, 1 dB step key site attenuators to vary, and my fixed pads here to set the input power dynamic range to my device. So I use these now. I don't use the instrument. And the same thing now, the output power of the amplifier goes back in. We use this to kind of make sure that we always get about the same level back into the instrument. So we're always measuring at a consistent range of output power, and we use the attenuators to set the input power. So we don't see the strange peaking effects that you sometimes get by using the attenuator in the instrument. So just, I don't know if yours does it, but awesome. So here's what I'm talking about here. This has a device hooked up, but I promise if I take the device out, you'll see the same exact shape here. So why is this frequency so peaky and this one is not? It's a function of the power level there. It's the source inside the instrument. You lower that power level from 13 maybe to 10, and they all start to look like this orange. This is a problem when you're measuring HBTs. You're measuring PHEMs, you're probably up here, so you don't see a lot of this. But when you measure the low additive phase noise HBTs, you have to be mindful of something like this. And one of the things we like to do is, how low is low power? How do I know I'm in small signal operation? How do I know I'm not exhibiting some type of nonlinear effect? Well, I want to intentionally drive my input power low, and it's obviously this is white noise limited here, right? It's obvious that nice flat line here. It kind of stops and gets flat. You're in the white noise region. Use this formula, and there's 14 references for it later, and you calculate the noise figure. You have to know the input power to your amplifier very accurately. If you know that and you measure the additive phase noise in the white noise region, you derive noise figure. And for low enough power, that will equal the noise figure you get with a noise diode. It'll be the same number. That's how you know I'm good here. And this is a great way to measure noise figure over power, because as you'll see, noise figure does not stay constant over input power. It changes. And that's something that we should really, thank you. I'll put the other glass of water there. It does change with input power. So it's something you want to be mindful of. So we start with this. All right, you know what? It's about right. I'm good. And then what you want to do is you want to start increasing your input power, because we want to see, are we following this behavior? Is our power spectral density, or is our single sideband phase noise improving as I increase input power? I don't know why they use P0 for input power, but it is. Okay, so here's that same LVA 273 PN. And we're starting here and we're increasing the input power in 1 dB steps. Now it is doing the right thing. It's improving. But if you pay careful attention, you'll notice that the increment between each step is not consistent. It's not the same. So if you increase the power by 1 dB and you get less than a 1 dB increase in noise figure, you're doing the right thing. If you increase the input power by 1 dB and the noise figure degrades by 1 dB, you haven't done anything. All right, nothing's changed. So you want to watch this, because what could happen, or what will happen, this happens to be a different amplifier, but it doesn't really matter. This just happens to demonstrate the effect I want to talk about at a power range that we have here. So what we did here is, this is now increasing, increasing, increasing. I get this optimum curve here, which is about plus 1 dBm in. Then I start to increase my input power above that. And what happens? Why am I going the wrong way? This says I should go down. Why am I going the wrong way? You're no longer in small signal. You're operating in a quasi-nonlinear region where you're starting to see the effects of AM to PM distortion. It's not the compression point. It's not, oh, if I do, you just go to the next slide. We'll talk about AM to PM in just a minute, but what we do is we map, or we calculate the noise figure as a function of input power for each device, and we compare that to a 1 dB per 1 dB slope. If you're under that 1 dB per 1 dB, your signal to noise ratio is improving with input power. And here you can see it's pretty much consistently under a 1 dB per dB slope, but it is increasing. Right? I started out with 8 dB noise figure. By the time, if I run this thing at plus 8, I got a 13 dB noise figure. You may want to take that into account in your cascade analysis, because it's not the small signal. If you're driving in these regions, your noise figure is changing. That in and of itself is something to take note of, because it will compromise your cascade analysis results. This one, you go past about here, you can see, look at this. That slope is much greater than 1 dB per dB, which means my noise is increasing faster than my power. And if you take a manufacturer's word for it, he's giving you this number here, right? He's not telling you this, all right? And then you're going to get the part and use it, and you're going to drive it here, and you're going to say, it doesn't make sense, something's wrong, I don't like this part. You're not going to understand, perhaps, why you're not seeing the performance that the manufacturer said. So you got to be mindful of this. Like I said, all right, there's not quite 17, but there's a few references for this formula here that you can go look up. This is plotted slightly differently, where we have now the 10 kilohertz offset over here and the 100 kilohertz offset over here, function of input power, and each curve is a different carrier frequency. So we happen to be looking at 2 gigahertz, which is the blue curve. So you can see I can run this as hard as I want, and I'm not going to notice anything. So just because you don't notice it doesn't mean the effect is not real. If you change the carrier frequency, so for instance, here's 6, 7, 8, you can see they all reach this inflection point. When you go beyond that, you start to degrade your additive phase noise, and it's happening faster than you're increasing your input power. So you're losing signal to noise ratio here. Again, why are we seeing this? Finally, all right, we come to AM to PM conversion. If you're not measuring this, and you're really interested in low phase noise, low additive phase noise, you have to add AM to PM to your standard characterization. It's not hard. The PNAs do it for you. You just have to ask it. So when we measure gain and all the S parameters and P1dB and third orders, we always add AM to PM, because I want to see these curves, because this is going to tell me where I can operate. This is going to tell me what input power I can hit those amplifiers with without getting this funny response in my additive phase noise. So we're going to look at examples next of each of these power levels. The thing that makes it frustrating is not all amplifiers. This is measured when you look at it as degree per dB. Don't look at phase versus input power. Look at the slope. So take a 1 dB section of input power range, get the slope of that line and plot that, then move it by your next point and plot that. So this is in degree per dB, and amplifiers will have this kind of a characteristic shape up to about here. What happens in this region is amplifier dependent. They don't all come down again. Some stay here, some come down. They don't all get worse with frequency. Some get better with higher frequency. So there's really no general suggestion I can give you. Oh yeah, run the blood. You can't. You have to measure this because each amplifier is unique. In this region, in the ultra saturated region, in the peak of AM to PM distortion region, and where this curve lies with respect to input power. And it's not really a good, P1 dB is not really a good indicator of how these curves are going to perform. And that makes it, so that whole thing will get a higher PSAT. I'm going to show you an example where a higher PSAT part has worse AM to PM than a lower PSAT part. So it's a little frustrating. It's annoying. We just have to measure it, and then we can pick where we want to operate. So we're going to look at a few different cases. We're going to operate the first stage here. Then we're going to move to this power level. We're going to keep our second stage roughly in this region here. Now, we're interested in 14.5. I can't measure at 14.5. Our instrument doesn't go that high. So we're going to look at 6 gig, which is, it's not even on here, but it's similar to the 7. The 6 gig curve is down about here. So we're going to use 6 gig because I can't measure 14.5. All right, so we're going to look at the cascade design optimization now. And here's an example of the input stage, right? We're going to run it at minus 8.2. This is our standard cascade analysis, right? I'm not doing anything fancy here. We have an input power. We have a small signal output power. These results are valid in small signal to a little compressed, but they're not really valid saturated, all right? But they are valid small signal to, 1 dB or so compression. They're going to remain valid. So I calculate my output power. I calculate my noise output power, right? The minus 174 plus gain plus noise figure. I look at that at the output, one hertz bandwidth. If you're doing system design and cascade analysis, you already calculate this number. You're doing this already. What you may not realize is that you're actually calculating the additive phase noise in the white noise region. You may know that, you may not. So what you do is after you have this power, you take a signal to noise ratio. I'm making it negative so that this is a negative number. So you calculate your signal to noise ratio based on the small signal power. And then this is S, basically. This is the S sub phi. We want L. So we're going to subtract 3 dB from that. So 163 minus 3 is about minus 164. I don't know if you can see it. What's that number? 164.9, 164.2. Not bad, right? So you've known this number the whole time, whether you realized it or not. You've been calculating power spectral density in the white noise region. You've been calculating the additive phase noise of your amplifier in this region. All you need now is one number. You need B sub minus 1, which I can, well, here it's noise limited, but it's about minus 150. I've seen this get down to about 152. It's very difficult to get these HPTs to get much lower than about 153, 154 because the cross-correlation gain indicator just doesn't go any lower. So you don't know what the real number is, but it's close enough. And then you're going to pass this output at plus 8. We're going to put an attenuator, and we're going to drive into the next stage at about plus 3. Now, if we go back, plus 3 at 6 gigahertz is roughly the 7 gig point. It's not a bad point, but it's starting to climb up that AM to PM curve. And again, we just go through, I don't know anything about phase noise. I go through my standard cascade analysis formula, and what do I get? I get minus 160.3. I have plus 3.3. I get 19.8. I'm a little compressed here. That's what I'm saying. So here we have to kind of understand that it's not exact because we are compressed here. But we calculate it nonetheless. We do our signal to noise ratio. We subtract 3 dB. I get 163. What do I see? 163.8. So again, it's pretty close. Good. We're not measuring it. We're using cascade analysis to model what the additive phase noise is. And if it's good to within a dB or so, you know what? I'm pretty happy. Notice you're starting to see the 1/F noise. See how it's starting to come off the noise floor here? Starting to rise. That's that 3 dB. That's that 3 dB increase in 1/F noise that Professor Rubiola predicts here. So you're seeing it here. You want to watch this region though. If you start getting crazy, you're overdriving something, and we'll see what happens then. So I don't like this operating point. If I was doing a system design, I don't like this. I'm white noise limited here, and I can tell just from my cascade analysis that I'm white noise limited. I don't like it. So I'm going to raise it. I'm going to come in at -2, and I'm going to come out at 14.5. Still small signal for this. It's still 3 dB below the 1 dB compression point, so it's still small signal. Do the same exercise. 153, 167.5. That's going to give me 170. Am I going to get 170? What do I get? 170.1. Well, this is not the device. This is a decorrelation caused by the phase noise analyzer sampling rate. It's not. Some of the newer ones get rid of that, but this one does not have that feature yet. So you have to kind of ignore this and get your white noise in a region where it's flat. So again, it's very good agreement, and I don't know anything about phase noise analyzers. All I need to know is standard cascade analysis and 1 point. I need to know this number like -150, and I'm happy. I passed that through, and again, we put now a 12 dB pad here. So I'm coming in at 2.5, and I get out about 18. But look at the improvement. Again, 160, I should get about 168.5. I'm getting 167.5. So again, it's pretty good agreement. And my noise figure only went up from 4.5 to 6.5. So you're seeing a little bit of an increase due to the increase in noise figure, but 5 dB improvement in additive phase noise here and a 4 dB improvement in your cascade. And my point is, well, do you care? Well, why wouldn't you? Why wouldn't you care? Right? Why wouldn't you want to get this as good as you can get simply by changing a pad value? Why wouldn't you do this? It doesn't make sense to me not to do it. Whether you see the effects or not is inconsequential. This is the kind of thing that should be incorporated into your cascade theory because it's easy to do and it's real. It definitely has an effect. And a block converter is perfect for this because it's one frequency. That frees up a lot of. I didn't talk about one feature of my favorite reflectionless filter. What you'll find when you do this over a wide band is that sometimes this input power over frequency wants to get less to avoid going into those high AM to PM regions, which means you need to slope your input power to have a negative going slope. We have equalizers that are matched. They give you a positive going slope. If you want a negative going slope, you can use a reflectionless filter for that. You find a low pass that's got about the right response, you use it in that region, and you get a sloped filter that's matched. You're not reflecting with a conventional filter back in. You're using a reflectionless filter to generate a negative going matched slope equalization. So you say, well, I'm not happy with 18, right? I don't like this number. You know, I need more power. So I'm just going to drive it harder. What could happen? Right? What could possibly go wrong? So here's our baseline state. I'm going to say, you know what? I'm going to drive him at -1, and I'm going to change this pad from -12 to, from 12 dB to 10 dB. What could possibly go wrong? I don't know. Did anything go wrong? Do you like this response? What happened to my 10 dB per decade slope? I've just pushed the white noise to 1/f cutoff frequency out by a factor of 4. Do you care? Maybe you don't care. Doesn't mean the effect is not there. Just because your digital loop doesn't allow you to see this doesn't mean that you're not operating here and you're not demonstrating this behavior. So again, we're only predicting here. And I know this 1 point here, but even look at this point, right? We about 150, yeah, it came up a little bit. Because again, we're still sitting on the noise floor here, but you would find that this may be affected as well. But my 10 dB per decade slope no longer holds, right? I'm 2.7, I'm 27 dB per 4 decades. I'm no longer 40 dB per 4 decades. So if you're a low phase noise guy, you want to know about this. Something's happening here that you're not aware of, or perhaps you are and you don't care, or perhaps you just missed it because you don't have a phase noise analyzer and this is in the noise somewhere. So what's the first thing you do is, well, I'll just change the part, right? I'm just going to change the part. I'm going to go to a higher power output part because, again, I remember this rule of thumb that said I should increase PSAT and I'll be happy. So we have an LVA 6183 PN, which is a derivative of the 273 PN. It's a higher power part, narrower bandwidth. similar noise figures, but about 3 dB higher compression point. And so I put that in with the same pad configuration. And what do I get? It's not bad. All right, it's not terrible, but it's not as good. Why isn't it as good? It's a higher power part, should be better. I don't understand if I'm really getting into the nuances of why this is not better. Oh, you got to go back to our friend AM to PM distortion. And these arrows are designed to kind of intersect with the 6 gigahertz curve, which is here. Okay, and the same thing here. 6 gig curve is this blue curve. So I've got a higher power part, higher saturated power, a little bit higher gain. All right, the gain, I can kind of expect the curves to be shifted to the left, right? I can expect the peak to maybe be shifted, which it is. But why would I expect the AM to PM to be worse in a higher power part at the same? It doesn't make sense, right? That's why it's very frustrating, because you have to kind of measure these things and pick your operating points accordingly. So let's kick the pad up by a couple of dB and see what happens. Look at that. Now I've improved. I'm better. I'm getting about a dB more out. So I'm getting my higher output power, but I had to change parts and change the padding. It's a lot of work, right? But if you want to really be a purist about not degrading your additive phase noise, this is the kind of trade-offs you have to run. Then there was that third region, if you recall. What if we operate in that really, really highly saturated region? Because that's another rule of thumb. Oh, just operate it saturated, you'll be fine. Well, not really. This part, notice, does not get significantly better in that region, where the other part we looked at came way down. So again, there's no general rule that says, oh yeah, if you run saturated, you will be better by default. That's not the case. We just demonstrated it here by example. All right, so we're going to look at +5 and we're going to look at +10. +5 is still very saturated. You know, we're not talking a little bit of compression here. But what you may have to do is you want to change the device operating point, because look how the AM to PM curves all improve with increased device voltage. Is this general? Of course not. That would be too easy. So you have to really evaluate each part. Maybe you want to change the current a little bit, but know that there are ways to improve this, but you have to, that's when you want a test board. All right, if you're down to this level of gory detail, you don't want a connectorized model. You want a test board so you can play with whatever voltage you want, set the current to whatever you want. That's what they're intended for. If you want to just see how they work and how it's going to work in my system with the, use the connectorized. You want to get into the nuances, you really need something like a test board. And look, you definitely see an improvement here. Maybe I'd run this guy at 8 volts. I go back, all right, 8 volts, this current, this kind of power with no resistance. I'm okay. We spec these parts very, don't tell anybody, very conservatively, all right? So you make your own calculations and you'll find that you can most likely operate pretty much wherever you want. And the part's still gonna last forever. What if you go to 10 volts? Now 10 volts, notice there's an improvement, but not quite as much. And I really have to bump up my voltage to 9 volts, and I'm still not quite as good. So I'd say, you know what? I probably don't want to run here. I probably keep it to something like this, adjust my voltage, and then, you know, if you see these numbers here, this is where's 10K. The cursor's on yellow. This is 165. So you're doing 167, 168 minus dBc per hertz at 10K. That's pretty good. That's very good, actually. So you can recover, say, the performance that you can achieve back here, but you may have to play with the operating point and find it out for yourself. So now, finally, the cascade. This is a busy chart. I apologize, but I like this chart. As I've been alluding to, if you're doing system analysis, cascade design, you've been calculating this power spectral density or this additive phase noise, whether you realized it or not. So let's take advantage of that. So say you had the luxury of calling up our applications department and say, Shraddha, can Joe measure this amplifier for me? And I probably will. No guarantee, but I probably will. And I give you a curve like this, okay, add a certain input power, you're good, all right? You can go back and using this relationship here, you can derive the noise figure because I know the additive phase noise. I can derive the noise figure. I take that noise figure, I go into my cascade analysis tool using that noise figure and the gain of the amplifier, and I calculate the output. I calculate the output noise power here, right? Here's the output noise power. I calculate that number. I take care of the 3 dB to convert it from S to L. I reference it to the signal power, and I get 174 dBc per hertz, exactly the number that I get from the actual additive phase noise. But I know something. I know the magic coefficient. I know B minus 1, all right, is minus 150 dBc per hertz. I know that number now. So now I want to analyze this whole cascade. This is everything from the VCO output to the ×2 input. I run my cascade analysis here. I'm using my Excel spreadsheet. I know my input power is +9. This region now. I know what that is now. I also know this point, and I know that I'm cascading 2 identical parts. So at a minimum, I'm going to get a 3 dB degradation in the 1/f noise. So I just moved this line up by 3 dB. This is, to a very good approximation, what you're going to be getting, even if you didn't have phase noise analyzers, if you were to look at this, this cascade. Then we go to the next phase. How do I know B minus 1? How do I get that term? And if you have a measurement, it's nice. If you don't, there are some rules kind of thumb here again that you can, at least for our devices, you can approximate using what I have here. But I want to point out a couple of things on this curve. These solid lines are all HBTs. They're all 2 micron emitter widths. The HBT geometry has not changed across all of these devices. It's exactly the same. And these operate anywhere from DC to 27 gigahertz. We're just adjusting the number of fingers. And you can see these curves are very consistent. These are all over the map in terms of frequency, performance, power levels. They're pretty consistent. And you can see for 100 hertz, this is where we kind of got, let's use a number like 150 to represent the B minus 1 minus 3 at 100 hertz for an HBT. These are all PAMs. Now, I guarantee you, I'll tell you right now that this part may have 5, 6, 8 dB noise figure. And some of these 0.15, 0.25 micron parts might have 1.5 dB noise figure. I'm not even seeing the noise figure yet on some of these PAMs. The 1/f noise is so high with those small gate length PAMs, I haven't even gotten to noise figure. I haven't hit white noise yet. So let me ask you, which is better? Is a PAM always better because it's got lower noise figure? Integrate the curves and ask yourself and find out. Integrate it and find out. Does this matter to you? Do you care? 1K or less? Maybe you don't for you. I've had synthesizers. I just care about a megahertz. All right, well, maybe then you can start to consider this. But boy, this thing hits noise floor at around 10 kilohertz. These don't hit noise floor till above a megahertz. So be careful with these rules of thumb. You have to know, kind of understand what they imply. So yeah, maybe if I get, over here somewhere, I might come below this curve. But boy, you better need the noise out there because you're taking a real big hit in the 1/f region. So these are guidelines. You can approximate, add 3 dB if you want to be, sure as to how to estimate the B minus 1 term. So you estimate that, you calculate the power spectral density in the white noise region, and you've just done phase noise analysis and cascaded phase noise theory. So again, if we go back to our example, if we include this in it now, this goes from the multiplier output to the actual input right here to the mixer. This is our final LO. Turns out this does not affect the cascaded noise figure and gain actually, because this turns out this is about 0 dB. So we can work with this number because if you look at the noise figure, I had 21.5. It goes to 21.6. If I'm worried about a 1/10 of a dB, I'm fine. All right. So this is about that curve. We increased it by 3 dB. Now what happens? We go through 20 log n. We all know that. Frequency multiplication, 20 log n. So the curves move up. I started at 6, not 14 and a half, because we didn't have 14 and a half available. So all these curves map up by 20 log n, and you get this new curve. But we forgot one thing. There's this preamp here. Happens to be a 0.15 micron preamp because I'm operating at almost 30 gigahertz. I'm kind of stuck with that type of gate length. Look at its 1/f noise. All right, I have to add these with power addition now. So I went through all this trouble of optimizing power levels and getting everything set perfectly, and this one guy comes along and kills everything. All right, but that's life, right? That doesn't preclude you from wanting to do it correctly, but be mindful that So you know what? I have the room, I have the power. I'm going to balance this. Maybe I'll drop this by 3 dB if you really. So there are things you can do, but just straight cascading, you're going to find that the last stage, right before the right before the mixer, is setting my noise floor up through, at least 10 kilohertz. Now, do I care? Like I said, in this case, we're using a digital loop. We know what its divided noise floors are. We are using a mimic-based VCO. I know what its phase noise performance is. I don't need it for this application. All right, you can see here's what we measured. Here's the mil spec I'm tracking against. If I wanted to do better than this, I would change that loop architecture, which we've done in the past. We've used sampling phase detectors and DROs, and you get this down considerably. And this PLXO from Axon actually performs very well. It's not expensive. It's very small. Performs very well. So in this case, I didn't really affect my output. But does that mean I shouldn't be mindful and consider some of these design features when I do my design? I don't think so. I think you should. What if, again, you have a nice SATA Labs $10,000 Sapphire stabilized oscillator? I don't want to kill this thing. I just paid $10,000 for it. I'm going to be setting the noise. This amplifier is going to be setting and this thermal noise floor is going to be setting my performance above 10 kilohertz. So I just wasted a lot of money unless I'm concerned about this close-in region. So that's the kind of trade-off you have to make. But it doesn't mean, again, that you shouldn't apply the theory. It's not that hard to do. I think we've shown it's pretty easy to account for a lot of this in your standard cascade designs if you don't want to go to fancy phase noise models and ADS. So that's the end. These are a bunch of references that I find useful. Again, you'll see Rubiola referenced a lot. If you're not familiar with him, I would definitely recommend you visit his website. He's got a wealth of information on pretty much everything. Some of these other papers here are equally as important, and some of these will talk about this large signal effect, this AM to PM conversion effect. Not in as gory detail as we go through here, and not as demonstrably as we do here, but you can see that some of the theory has been discovered in some of these papers here. And then if you go to our website, we have 4 now webinars that you can watch. And we just put this last one up. This has a lot more information in terms of different device types. We have different types of HBT designs, different types of preamp designs, and you can see the differences in additive phase noise and AM to PM performance across more device types than we have the time to explore here. So anyway, if you're interested, take a look or call applications. They'll get a hold of me. And thank you for attending. Hope you learned something. All right, see you soon.